This video we are going to begin our section 1.3. For most of the DEs that we're going to solve in this class, they're going to be solvable. Now with this, and you guys you've been in mathematics long enough and your physics classes to understand that a lot of these types of problems you're not going to see in the real world at all. The real world is never this pretty. Most of the things that you're going to be doing as an engineer, if you are working with actual mathematical models, is you will be taking what we call a numerical approach. This is all based on approximations. So I'm going to show you a numerical approach to solving a DE. It's very approximated. And you'll see what I mean by that. So if we have it in this form, recall that this dy dx is a derivative. It is our slope at a point. So we could actually draw a full graph at every single point, and we can capture what the slope looks like at that point, and then try to do our best to make a picture from the slopes. I created a table for you, but you'll have to make a table if you're doing these types of problems. And there are patterns to this. So let's work on seeing some of those patterns. So what I usually do is, especially if I'm adding, so here's just taking my two numbers and adding them. 4 and -4 make a 0. 3 and -3, 2 and -2, 1 and -1, 0 and 0, and so forth. So this whole diagonal, we get zeros. You can probably tell what pattern I'm going to start looking for now. 4 and -3 is a 1. So I get 1s. Here, if you look, 3 and -2. I'm just adding them all together, so I'm going to get a 1 all the way down the diagonal. Then I get a 2. You can check these. Alright, so plugging these numbers in, and they're just going to go negative the other way. It's probably the most annoying part of this. It's not going to always be like this. If you think about if this formula here is not just adding two numbers together, we could start getting some crazy numbers throughout this. Alright, filling these in. There we go. Okay, so we have a measure at every single point. Let's let this be our x, this be our y. And what we're going to do is all these numbers represent the slope at each point. So, for instance, at 0, 0, if we use this table, this tells us that m is 0. Because when I add them, I get 0. So we're going to put a small flat bar that tiny line has a slope of 0. We also can see that we have a bunch of other points that are like this. We have -1 and 1. So we're going to have a flat line there. And all the way down this diagonal, we're going to get a bunch of slopes that are 0. So we know that our graph, if it passes through this diagonal, it's going to have a slope of 0. So it's going to flatten out some. Now we can take the next set of lines that are the 1s, and I identify, okay, so this is a 4, -3. So 4, -3 tells me that I have, okay, if I add those together, I have an m equals 1. So at +4, -3, I got a 1. So at every one of these diagonals, we get a 1. You want to try to be decently accurate because our slopes are going to slightly change, and it's going to be pretty difficult to tell the difference between these lines. Alright, there we go. Slope of 1 all the way across, and then as we go over, we'd have a slope of 2, so the lines just get just a bit steeper. So this is what I was talking about here. You want to slowly get steeper because our slopes are going to slowly get bigger. We don't need to go all the way out. We just have to go through 4. So we can just take these away, meaning. There we go. All right, then the line gets steeper. Let's go to 4. And then the next diagonal gets steeper. Steeper. And then still getting this diagonals even steeper. As you can tell, it's a bit hard to do there. All right, on the other side, we have a negative 1. So we get a bunch of diagonals that look like this. All right, and then at negative 4, 3. So negative 4, 3. It's a negative 1. Oops, I think I counted wrong. Okay, so it's going to get even more negative. So all these diagonals are going to start getting steeper. So every diagonal getting a bit steeper. So really these are just super time consuming. So as we get towards the corner, try to make your lines a little steeper. Okay, so there we go. Okay, so this is called a direction field or slope field. So everywhere in this slope field, it will give us a direction. We actually see these quite often in vector field, stuff like that. Your radar maps for weather, you start seeing these maps just a bit. So what we're going to do now is we're going to use these slopes, and we have 4 different answers here that we're going to try to map out. The first one, we're going to put a point, and we're just going to follow the slope. So this says go flat, and then it says it's going up. And it's going to go up like that, looks like. When it comes back this way, it looks like it's going to start, it should be curving up. Oh, I think I have my orange. Oh, I do. Okay, so we're going to go through and do these again. Those are all negative 1. I have them the reverse way. Some of you guys may have already caught that. All right, so going negative 1. These are time consuming. There we go. Now we just make the lines, every diagonal, we just try to make it a little steeper. All right, so there are really steep lines getting down here. There we go. Now the picture looks a little better. Sorry about that. All right, so now graphing this going now makes sense. This is going to go up like that. So that's our first curve. Put a red dot here. So that's that curve. The next curve, I start at negative 2, 2. So I just, negative 2, negative 2. I just put a curve down there. And then I just map out where this is going. So this is going, it looks like, came from up this way. And it's going to go down like that. So that is that second curve. I should have picked a different color. All right, this one's starting at 4, 1. Looks like it's going to probably shoot up like that. And then if I'm following this, looks like it came around and shot up that way. So these are all solutions to our DE. But as you can tell, they're like super approximated, meaning like I can't write down one of these curves. Now, I want you to notice this one. I want to point it out. It's on that dotted line. This is actually a solution to that curve then. So to that IVP, if I use that straight line, it should be able to solve that DE from up here. So each one of those curves, if we were to try to write a formula for it, if we could model something for it, it should solve this. So a numerical method fits best in the real world. What you'll actually do is maybe you can measure wind speeds, and then you could maybe map out a position function for a storm, stuff like that. Be very careful. Try not to make that mistake that I made right in there. I had my slopes flipped. It happens. So just be very careful. How I caught it is I could tell like our slope field didn't really make a lot of sense once I tried to graph something with that. Now with all the orange tick marks, it's like flowing. It looks fluid.